Hello everyone, welcome to video number 7 of AP Computer Science A. The main topic for this video is runtime, and we will also throw in some recursion practice along the way. So let's start off by introducing two fast sorting algorithms. The first one is called Quicksort, and this is a diagram of how it works. So how it works is it chooses an element as the pivot. In this diagram, it always chooses the last element as the pivot. And what it does is it scans through the collection, comparing each element with the pivot and deciding whether each element should go to the left or to the right of the pivot. And after one iteration, it uses recursion and repeats the same process to sort the left and the right of the pivot. So now that you know how Quicksort works, let's see an implementation of it. So Quicksort is pretty difficult to implement in Java because you need a way to merge lists together, and in Java there's no easy way to do that. So we're actually going to be implementing it in Python, because with Python you can easily merge two lists together by adding them. So I'll walk you through the syntax of Python as we go along. First we need a function, and the way to do that is to type def, which is short for define, the name of the function, which I'll call sort, and then in parentheses the parameters. You don't need to tell Python the types of parameters, you just need to give each parameter a name. I'll call our list x. All right, and then colon, and then you can begin making your function. So first, the base case. If the length of x is 0 or 1, then we don't need to sort it, we just need to return x. So if, to find the length of a list, you type len, and then the name of the list. So if length equals 0, or length equals 1, then we just return x. And otherwise, we need to sort it. So we need 3 lists, and the way to declare a list is to write the name of the list, and then equals, and then brackets, and the elements inside the brackets. And we don't need any elements for now. So the first list that we need is for the elements that are less than the pivot. The second is for the elements that are equal to the pivot. And the third is for the elements that are greater than the pivot. So now, to scan through each element of the collection, we can use a for each loop. And the syntax for that is this: for a variable, and then in the name of the list. So we do if a is less than element length of x minus 1 of x. So this is basically the last element of x. Then we add a to the left. So to do that, we type left.append a. Right, and then if a is greater than the last element of x, then we add it to right. And then the last case is if it's equal, so we type else same.append a. And keep in mind that this should be else if, and you can just type elif, you don't need to type the whole word else. All right, and then after this for loop, we just return. So we first need to sort the left side, and then we merge it with same, and then we merge that with sort right. So that's our function. So now let's just sort a collection. All right, and it sorts it properly. The second sorting algorithm is called merge sort. And the way that works is each element starts as its own individual group of one element. And these groups, every adjacent pair of groups is merged into a larger sorted group. And then this process is repeated, so every adjacent pair of groups is merged into a larger sorted group until the entire collection has been merged together. Now you might be wondering, how do two groups merge together? So how do you go from here to here? Well, let's see an animation of how that works. So you have two scanners that each start at the beginning of each group. All right, so let's see the animation play. All right, so each scanner just goes from left to right, and each time the elements of the two scanners are compared, and whichever one is smaller, that one is added to the list. So the implementation of merge sort is actually pretty difficult, so I'm not going to show it in this video, and you don't need to know how to implement quicksort or merge sort for the AP exam. You just need to know how quicksort and merge sort work. If you need to sort a collection, there's no need to worry, because Java and many other languages have already coded up a sorting algorithm for you. So in Java, if you need to sort an array, then you do import java.util.star, and then in the code you say arrays.sort and then the name of the array. And that will use quicksort to sort the array for you. And if you needed to sort another type of collection, such as array list, then you would say collections.sort instead of arrays.sort. So let's just verify that this works. So this for each loop prints out every element, and you see that it's sorted. Here is an optional exercise. Create a program that takes an int n as input and prints the nth row of Pascal's triangle. So how Pascal's triangle works is each element is the sum of the two elements above it. So this 2 right over here is 1 plus 1. So if you want to give this a try, then pause the video here. The solution will follow in 3, 2, 1. In order to determine a certain element of Pascal's triangle, you need to use recursion. So let's create a method. It's going to return an int because every element of Pascal's triangle is an integer. And we have 2 int parameters, row and column. So to give you an idea of how indexing works, the 1 at the top of Pascal's triangle is at row 0 and column 0. The 2 that shows up in Pascal's triangle is at row 2 and column 1. So we have 2 base cases. The first is if we're at the leftmost column. So if column equals 0, then we return 1. The second is if we're at the rightmost column. So if column equals row, then we also return 1. Otherwise, we return the sum of the 2 elements above. So that would be Pascal row minus 1, column minus 1, plus Pascal row minus 1, column. So now let's implement the main method. We need to print out at row n and going from column 0 all the way up to column n. So for int a equals 0, a is less than or equal to n, a plus plus, we print out Pascal row n, column a. And it prints out the correct answer. But now, let's try a larger number. So this time I'm going to give 30 as the input. And you can see it's taking quite a while. So how do we make it faster? The answer is to make it stop repeating the same calculation so many times. And what I mean by that is, if we're going to give 30 as the input, then, for example, the program will have to print Pascal 3024 and Pascal 3025. And Pascal 3024 is equal to Pascal 2923 plus Pascal 2924. And Pascal 3025 is equal to Pascal 2924 plus Pascal 2925. And notice how I said Pascal 2924 twice. So with the current algorithm, we have to calculate that value twice. So what if we just store that value the first time we calculate it, so the second time we call it, we don't have to calculate it again? That would make our program a lot faster. So in order to store our memory, we need to use a 2D array. So in total, we have n plus 1 rows because we go from row 0 to row n. And we also have n plus 1 columns. So now let's make the 2D array a parameter of our method. So one case is if memory row column is equal to 0, which is the default value. That means that the value we're trying to find has not been calculated yet. So in that case, we have to set memory row column to this value right over here. All right, and then afterwards, regardless of whether we had to calculate the value we're trying to find, we can just return memory row column. So what this does is if the value we're trying to find has already been calculated once, then we don't need to calculate it again. And now let's make sure to change all of these methods. So now let's run this and try 30 again. And this time, it takes barely any time to print everything out. So now we're moving on to the last topic for this video, which is runtime. And runtime is not a topic that will be tested on the AP exam. So even if you don't understand anything about it, don't worry. But I'm including this section in this video because some of you are probably curious and because runtime is a pretty useful concept in computer science. So runtime depends on the number of times a process is done. If a process is done n times, then the runtime is big O of n. That's just the notation they use for runtime. If a process is done n squared times, then the runtime is big O of n squared. And n is a large number because if n was small, then it wouldn't matter because the program would be fast anyway. So if you had like n equals 5, then this would be big O of 5 and this would be big O of 25. And either of those can be done in an instant by a computer. So we're talking about like n equals 10,000 or n equals 1,000,000, something along the lines of that. So here are some examples. What are the runtimes for the following codes? I'm going to go over the solutions one by one, but if you want to give all 4 problems a try, then pause the video here. If you're stuck, then I would suggest looking at the solution for number 1 and then trying problems 2 through 4. But anyway, pause here if you want. The solution to number 1 will come in 3, 2, 1. So the answer is big O of n because this for loop is run n times. So now on to number 2. The solution will come in 3, 2, 1. The answer is big O of n squared because the outside for loop runs n times, and each time it runs, the inside for loop also runs n times. So in total, we have n times n, which is n squared. So now on to number 3. The solution will come in 3, 2, 1. So the answer is big O of log n because we start with a equals 1, and then a becomes 2, and then 4, and then 8, and then 16. So a grows exponentially. So as such, it would only take log n runs of the for loop before a reaches n. So now on to number 4. The solution will come in 3, 2, 1. All right, so this was pretty similar to number 1. So number 1 said that a is less than n, so it had a runtime of n, and now this says a is less than square root of n, so therefore the runtime will be big O of square root of n. So here are some key concepts. So first, when you have the sum of several terms, you only need to keep the largest term. For example, if you had big O of n squared plus n, that's basically the same as big O of n squared, because n squared is a lot bigger than n, so n squared and n squared plus n don't have such a big difference, and so therefore you can remove the n because that would make it easier to read. And second, coefficients can be ignored. So for example, this for loop is run only n over 2 times because we have a plus equals 2. However, the runtime is still big O of n. And the reason for this is because n is really large. So if you had like 500,000 compared to 1 million, the difference between those two numbers isn't that big. But if you had like n, which is 1,000,000, and n squared, which is 1,000,000,000, that is a big difference. So therefore, you need to keep exponents, but you can ignore coefficients. So now we're moving into the runtime of sorting algorithms. Let's start with selection sort because that's the easiest. So with selection sort, for each location, you have to scan that location and everything to the right. So you start with the first location and you scan that location and everything to the right. So that is n scans. And then you go to the second location and scan that location and everything to the right. That's n-1 scans. And then the third location, you scan that location and everything to the right. That's n-2 scans. And this continues all the way down to 1. And this series can be written as n times n plus 1 all over 2. And that is a runtime of O of n squared because n times n is n squared, and n squared over 2 is still an n squared runtime. So the best, average, and worst case performance of selection sort is O of n squared. Now moving on to insertion sort. So insertion sort, for each element, it would have to move it back until it falls in the right place. And the average number of times each element is moved back would likely be n times some sort of constant. And remember that constants can be ignored. So since you have n elements and each element would have to be moved back on average n times a constant times, that means that the average and worst case performance of insertion sort is O of n squared. However, in the best case, consider this sorted array right here. In that case, we wouldn't have to move any elements back. We would just have to scan through this array and see that it's sorted. So therefore, the best case runtime of insertion sort is big O of n. And now for bubble sort, so each iteration takes big O of n time because it scans through the whole thing. And how many iterations are there? Well, that depends on how out of place the elements are, but for a larger set of data, there would likely be some elements that are pretty out of place. And that means that bubble sort will take on average n somewhere near n iterations. So that means that the average and worst case runtime of bubble sort are both big O of n squared. But the best case, if the data is already sorted, then there would be only one iteration. And that means that the best case performance is big O of n. And now for quicksort, so each time you choose an element and divide the data set up, it will divide it up likely pretty evenly. So we can say that it divides it approximately in half each time. And if it divides it in half each time, then it would take log n iterations of quicksort until we've broken everything up. And each iteration takes big O of n time. So therefore, the best and average case performance of quicksort are n log n. However, quicksort can be as slow as big O of n squared. If you consider the example that we used earlier, where you always choose the last element as the pivot, consider what happens if the data is already sorted. We start by choosing 7 as a pivot, and we find that everything to the left is lower than 7, and then we choose 6 as a pivot and find that this is all lower than 6, and then we choose 5 as a pivot, and then 4, and then 3. So that will actually take n iterations. So in order to prevent the worst case performance of big O of n squared for quicksort, you need to choose a good pivot. And that's something that's more complicated that we're not going to get into for this video. Now for merge sort, so each iteration of merge sort takes big O of n time. And how many iterations are there? Well, with one iteration, you can merge groups of 1 into groups of 2, groups of 2 into groups of 4, groups of 4 into groups of 8. So the size of groups grows exponentially. Therefore, it would take log n iterations of merge sort before we've merged everything together. So therefore, the runtime of merge sort is n log n. And now we're done. The most important thing to remember from this video is how quicksort and merge sort work. Everything else we did, from making a program faster, as we did with the Pascal triangle printer, and runtime, those are mainly optional and will not be covered in the AP exam. However, I hope they were fun and educational. And with that, I'll see you in video number 8.